Hello everyone, welcome to the first video tutorial, which I'd like to go over very high level overview of the chapters in the linear algebra book. So what we'll do is basically go through the table of contents and trace what's covered in the book, and in the same time certain things are kind of useful if you show by example. So what I have here is a Jupyter notebook which we can try some of the numerical examples. So chapter 1, Math Fundamentals. This is really a prerequisites chapter. You kind of need to know basics about numbers, functions, and basic rules of algebra. In case you don't know, this is the chapter for you. It will review all these basic things like how to solve equations, quadratic equations, different types of functions. So good to check out. Maybe you're a little rusty, check out chapter 1. Then we have another chapter on vectors. So what is a vector? So I won't explain what's going on here, but I'm using this package called SymPy, which is a computer algebra system, and it will allow us to show some numeric example with vectors. So here's a vector. Vector is a mathematical object that has two coefficients, the x coefficient and the y coefficient, or the first and the second, any way you want to think about it. And here's the other one. And this is how you represent them graphically. So the black vector is is here. And geometric, you can think of this vector as telling you to go 2 steps in the x direction, 1, 2, and 3 steps in the y direction, 1, 2, 3. So that's how you get the black vector, the graphical representation of it. By the way, vector comes from Latin vehere, to carry. So indeed, you take the point and you take it 2 steps to the right, in the x direction, 3 steps in the north. That's the other vector, is just 3, 0. What happens when you add vectors? You add their coefficients. So the sum of the x coefficients is 5, the sum of the y coefficients is 3. Not super exciting. Let's see that graphically. So you take first the black vector, and then you take the blue vector after. So the combined displacement, the combined vehere, carry, is equivalent to the red vector. So chapter 2 is also about it's a review of vectors, and really goes into the details. But one thing I really want to talk about, and will be useful with these graphs to show, is the notion of a basis. So a basis is perhaps the most important concept throughout the book, in the book. And it's really worth talking about it a little bit here. So what is a basis? A basis is the coordinate system you use to describe vectors. So let's say I talk about the vector 4, 6. So this says go 4 steps in the x direction and then 6 steps in the y direction. But it doesn't need to always be the x and y directions. The directions could be arbitrary. So in this case, if you want to be precise, I should say 4, 6 with respect to the standard basis. What's the standard basis? Well, that's the standard basis. You have I hat, which is 1, 0. That's a unit step in the x direction. And j hat is 0, 1. So that's a unit step in the y direction. So I and j. This is I. Whoa, this is I, this is j. Now, let's look at that. Instead of my fingers, it will be easier to show it here. So that's the vector 4, 6. Means this is the expression I want you to look at. It's go 4 times in the I direction, 1, 2, 3, 4, and 6 times in the j direction, 1, 2, 3, 4, 5, 6. So that's how you get this vector. Now, interestingly, the same vector v, this vector, it could correspond to a different coordinate pair. So this is, if we use the basis 1, 1 and 1 minus 1, it would be a different coefficient. So, I won't explain it too much. I'll show the example here. So using an alternative basis, which we call b prime, we have the vector 1, 1, and the vector 1 minus 1. Let me show you. So this is the vector 1, 1, this is the vector 1 minus 1. And the same vector here, the turquoise one, to get to this point, in terms of these directions, I would have to go 5 steps in the b1 direction. And instead of going in the b2 direction, I go minus 1 the b2 direction. And then the combine of these vectors is this turquoise vector. So the coefficients, I would have to say, to describe the same vector, I would have to describe it as the pair 5 minus 1 with respect to this basis. So why I'm talking about this is that it's not so simple, perhaps until now, when you talk about vectors, you talk of them as coefficients, and you didn't really, the basis was always in there. But in linear algebra, we have to be really precise. So when you talk about a given vector of coefficients, you have to say coefficients with respect to which basis. So that's although chapter 2 is supposed to be basics and review, we really focus on basis, on the notion of basis. Next, chapter 3. I guess linear algebra really starts here. So the main objects of study are introduced. We have vectors and matrices. You can think of vectors as lists of numbers, arrays, and matrices as tables. You know how in Excel you have different rows and different columns. Well, here a matrix is analogous to an Excel sheet. And notice the weird notation we use. So we call, for example, this one is the third row and the second coefficient. So that's how we refer to the entries of a matrix in general. So chapter 3, we'll define, we start off when you introduce a new concept, like a vector or a matrix, you have to define the operation. So for numbers, you know how to do addition, subtraction, multiplication, division. For vectors and matrices, we have different operations. So let's look at them here. Addition, subtraction, scaling. And there are two types of product for vectors. So if you've never seen these before, this is the chapter, this is the time to look at them. And same for matrices. We have addition, subtraction, matrix vector product, very important, matrix product, the matrix inverse, trace, and determinant. So it seems like a tall list of things to learn, but the good news is once you learn these operations, there won't be anything new in the book. So we're going to just learn about implications and applications of these operations, but it won't be like randomly introducing new material in chapter 5 or chapter 6. This is it. Really, linear algebra, the point of linear algebra is to get you comfortable with these new mathematical objects. And why? Well, another important thing is the notion of a linear transformation. So what is a linear transformation? Think of it as a function. But instead of a regular function that takes numbers and produces numbers, so that's the high school type of function. Now we have vector functions. So the input is a vector and the output is a vector. So in a way, this is perhaps the most important part about linear algebra is how to manipulate vectors. So these are the type of useful transformations you can do in vectors. And although we'll talk about them in great detail in chapter 6, but even before then, it's so core to linear algebra that we're introducing them right away. And in particular, there's a strong relationship between linear transformations and matrices. So why is that? Because in general, you can think of arbitrary vector functions, but here we restrict, in this whole book, we'll restrict our attention to linear transformation. So what is a linear function is one that when you input, this is called a linear combination. So it's some coefficient times one vector plus another coefficient times another vector. The output looks like the same linear combination. So the coefficient times the output of the first input of the first vector and b times the second output. So this structure is very useful. And in particular, it allows us to establish this really important relationship between linear transformation and matrices. So any linear transformation that takes n vectors as input and produces n vectors as output, because of this property, it turns out we can write it as a matrix vector product. So what is a matrix vector product? Well, we'll define it in more detail, but somehow, whenever you talk about linear transformations, we can talk about matrices instead. So this is the abstract mathematical notion of a linear transformation, and this side represents the practical computational technique. So a lot of the problems you will solve, you're really talking about transformations, but thanks to the matrix representation, we're able to manipulate, we're able to do computations with them. So, we don't joke around with chapter 3. We start right away with the core ideas. So there will be no beating about the bush. So here is this table of important properties. All right, so this is, I'm just scrolling through the chapter, but we've reached chapter 4. All right, so let's keep the pace so we can keep this within reasonable time. Computational linear algebra. What is this all about? Well, we start with the algorithm. So there will be a lot of theory, there will be a lot of geometry, functions, theory, but in the practical aspect of linear algebra is you have to compute stuff. So you, at some point, you'll have an exam, and they'll be like, solve this system of equations, or find this matrix inverse. So I want to make sure that you know this really well. So we start the book with perhaps the most boring and the hardest part, but we start with the most useful part also. So first on topic is this procedure called the Gauss-Jordan elimination procedure. So it comes up whenever you have systems of equations like this. So let's switch to the notebook. It will make the explanation easy. So you have this system of equation. You have two unknowns, x1, x2, and you're told that x1 plus 2 times x2 equals 5, and 3 times x1 plus 9 times x2 equals 21. Find x1, x2. So this is called a system of linear equations, and it's a standard type of problem which you're supposed to know how to solve. In fact, you could subtract this from this. There's a lot of things you could do. In high school, you're supposed to know how to do this. But now we're not in high school anymore. We're going to use linear algebra, and we're going to use a matrix. So this is what I'll do, is I'm going to rewrite this equation in this form. This is called an augmented matrix. And basically, I ignore the variables. I assume the first column is for x1, so I don't need to write x1 all the time. And the second column refers to x2 coefficients, so I'm not going to write it. and then the third column are the constants. So why do this? Because now I can do really useful things. For example, let's say I want to add this equation to this equation. I can do that just with the numbers, right? The coefficients are the same in each column. It stays constant. So now I want to keep the video short, so I'll just show and try to explain as we go along. So I would like there to be a 0 here. So to simplify, get rid of the x1, I can subtract this row from this row 3 times. So that's what this expression does. It says make the second row. So this is a little weirdness in Python. We use zero indexing, zero-based indexing. So 1 refers actually to the second row, just so you're not weirded out by this. So this is saying make the second row equal to itself minus 3 times the first row. So indeed, that's what happens. So I'm allowed to do this because I'm allowed to do this with equations, like, right? If this equation is true and this equation is true, then subtracting them one from the other is still a true system of equations. Now I want to make a 1 here. Yep, so I just divided the second row by 3. Now I'm going to subtract this from here twice. So subtract the second row from the first row twice. All right, so I did these 3 row operations, and each of them did not change the solution. I am allowed to do this with equations, right? And then I have a new system of equations, which if I copy it into the standard form, it says x1 equal to 1 and x2 equal to 2, which is kind of what I wanted to. Now I found the solution. So that's how far I wanted to talk about this, but this procedure for getting rid of coefficients and then subtracting coefficients up is called the Cauchy-Jordan elimination procedure. So it's one of the first and most useful computational aspects of linear algebra, and the book goes into significantly more detail and describes the different row operations you can do, and describes the algorithm, and there's important special cases. So here we had one solution, but it's also possible to have infinitely many solutions, and you read about it because it's not just as simple as shown. Of course, yeah, I show you the tricks too. Now, matrix equations. So there's not much demo to do. I just want to show you what happens if you have this equation. So, I mean, first of all, let's look at the numbers. If you have AB equal to C, and then these are just numbers now, and I say solve for A. So you would say, well, you know what? I'm going to divide by B on both sides, right? If you want to get rid of B. But it's not as simple. So with numbers, you can do all kinds of things. You can say it's divided by B, 1 over B. Division by B is something that makes sense, right? In matrices, we don't have division. What we have is a matrix inverse, which kind of acts like division, but you have to be clear which side you act on. So in numbers, you can divide. It doesn't matter if you say C divided by C times 1 over B or 1 over B times C. In matrices, it matters. So if you want to solve for A here, so if you want to isolate B, like this makes no sense. You cannot write that for matrices. You have to talk about the inverse. So this is called the matrix inverse, and the right solution is this one. So we hit both sides of the equation by B inverse, and what you get is C times B inverse. So that's a little bit new. So without going into detail how to find the inverse, which we'll talk about in a second, there's this notion that matrices are not matrix product is not commutative. So let's just look at some pictures. So you have A times X equal to B. If you want to find X, you have to hit by A inverse on this side, and that's how you solve. Same here. If you want to find A here, you have to hit by B inverse on the other side. If you want to find B, you have to hit by A inverse. So that's the core idea. Is this? If you have A times B is not the same as B times A. For matrices, it's called a commutative. Like if you can change the order of the operands, the operation is called commutative. Matrix multiplication is not commutative. So it's so important that I have like 2 complete sections on that. They describe how matrix multiplication is done. So let's look at that here. We have 2 matrices. A is a 3 by 2 matrix and B is a 2 by 2 matrix. So when I do the product of the two, I get a 3 by 2 matrix. And look at the coefficient. So the first coefficient, I mean, you can look in the book too, but imagine the first row of the matrix and the first column of this matrix. So this one and this one. And what goes in the entry is the dot product. So A times G and B times I. So this is how matrix product is computed. For people who know Python, this would be the operation, just to show you that you have to go through each entry and each row, each column to get the right answer. Notice you cannot multiply everything. If you try to multiply B times A, so in the opposite order, there's a problem. There is not that they don't have the right dimension. So Yeah, so details about matrix multiplication, we have a whole chapter on that. Next topic, determinants. Really, without going into too much detail, here's a matrix A, and the determinant is equal to this product of AD minus BC. Why? Why this formula? Well, it has some useful geometrical properties. For example, let's say you have these two vectors. Here you have the black vector and then another vector, 2, 2. And in addition to them, I add another copy. So wherever the black vector ends, I add a copy of the blue vector, and wherever the blue vector ends, I add a copy of the black vector. So this parallelogram, what is its area? Think about this. Well, the standard formula for the area of parallelogram is 3, so the base, the length of the base, times the height. The height is 2. So the area of this region here is 6. Well, guess what? If we were to put these vectors 3, 0, and 2, 2 in a matrix, and then compute its determinant, we get 6. So it's the determinant in 2D is a useful way for computing this kind of, if you have two vectors and they get squashed a little bit, what is the area that they enclose? I won't say much more than this, but there's a whole chapter on that, which goes into the computation. So this is a standard thing on an exam. They'll give you a matrix and say find its determinant. And there's a formula for 3 by 3, which is a bit more involved. So for 2 by 2, it's an area. For 3 by 3, it's a volume of a parallelepiped. Yes, I just said that. Oh, yes. Then there's some properties you should know about. And in general, determinants are an interesting topic, which we won't talk about much further. Matrix inverse. Now we get to the major one. Whatever A is, so A is some matrix, A is some transformation. If it's invertible, then there is a undo operation, A inverse. So think about this. So you have vector, and A is acting on the vector, but then you say undo. So what you get back is the vector itself. So if you just scratch the vector, think of the two operations on their own. It's like this is an operation, this is the opposite operation. So the combination is the identity. So this matrix looks like it's the identity transformation. Whatever you input, the same thing comes out. And it's interesting that you can do the undo operation first, so pre-do or pre-undo, and then if you do the operation, then again, it's the same thing. So the inverse doesn't matter if you act from the left or from the right. The effect is to obtain the identity transformation. So let's look at an example. It's a matrix we saw before. So I say here, right, matrix inverse doesn't always exist. So before we try to look for inverse, we want to check if an inverse exists. So we'll talk about later matrices that don't have an inverse. So a good way to check is check the determinant. Determinant is non-zero, means the inverse exists. So let's find it. Right, so this transformation, whatever input the input is, it does some mixture, linear combination of the input, and this operation will do the opposite. So the combination of the two is the inverse transformation, is the identity transformation. So imagine you have here x1, x2, then x1, x2 will come out. All right, but we're not here to talk about theory, right? We want to know we're in the computational linear algebra section, so we got to know how to compute these things. So in fact, the whole chapter gives you different formulas, some of them quite serious, how to compute matrix inverses, in the case 2 by 2, 3 by 3. That's the 3 different ways, and I have the example right here. So let's look at the example. So obviously the easiest way is, as I showed, is if you're on a computer and you just call the inverse method of the matrix and it shows you the inverse. But what if you're on an exam and you just have pen and paper? So one formula is to compute the adjugate of a matrix. I won't go into details, and then divide by the determinant. So that works, you get the same answer. Another way is to reuse what we learned in 4.1, the reduced row echelon form. So you write this matrix. Imagine you put the matrix A here in the left half, and you put the identity matrix in the right half. So this is an augmented array of twice the dimension, right? It's whatever the matrix size is, and then an identity matrix next to it. And now you start doing row operations until you get this into the reduced row echelon form. So that's how you get that here. And what happens here, in the right-hand side, you will have the inverse. And if you want to extract that, you can call this operation, and you get the inverse, which is the same as this one. So this is the most practical one. If you're in an exam, this is the one you can do on pen and paper. This is a little mathematical detail. Is all these row operations we perform here can be represented, it's the same operations, can be represented by these matrices. These are called elementary matrices. So if I was to multiply any matrix by this matrix, the effect will be to take the first row and subtract it 3 times from the third row. You can read about it in the book, but let's see what happens here is these 3 elementary matrices acting on A produce the identity. And recall what we said in the definition of the inverse is that the inverse is whatever multiplies A to give the identity. So in this case, we have bad LaTeX rendering. right? So the inverse multiplying A gives the identity. And in this case, we have these three matrices together times A, they give the identity. So it turns out this must be the identity, the product of the elementary matrices. So now you have it. There's three different computational techniques that could be asked of you on an exam, and you could do it with pen and paper. That's the computational chapter. I'm tired just talking about it in the overview. Imagine how tired you'll be by solving it. But you know what? If you solve these problems here, which are not that many, you'll be done with chapter 4, and then we can do all the cool stuff. Chapter 5, geometrical linear algebra. All right. This overview has already taken 30 minutes, but bear with me because we're getting into the cool stuff now. So geometry, right, so we learn about vectors sort of algebraically, but the geometrical aspects of vectors are kind of important too. It's what you can learn, intuition. And so this is a point. Again, it's a bit like a vector, just 3 coefficient tells you a coordinate point. And this is a line. So what is a line? You say, it's a description, one description of a line is to say it passes through the point P, P naught, and goes in this direction V. So, for example, let's say the point is here, and this is the vector V, so that, if you go 2 times there, it's the whole set of points that are multiples of V, in the starting at P and multiples of V. So it describes that's a line. A plane, you can define it in a couple of different ways, but in general it's some equation in R3 that's satisfied. So x, y, and z have to satisfy this equation. So we can plot some plane here, just to give you an example. So these geometrical objects, points, lines, and planes, are useful in all kinds of situations. So this is called analytic geometry. There's a whole chapter on that. What if you want to find distances between them? What if you want to find parallel planes, closest points? There's all these computational aspects, geometrically, problems that can be asked, can be stated in terms of geometry, that you can use your vector techniques to solve them. So that's roughly what chapter 5 is about, all this geometry stuff. The only operation I'll talk about is the projection. So projection is bread and butter, and it will come up several times in the book. So let's say you have some input vector V. Do I have a picture of it? Not particularly. You have some vector V and a direction D, and that's how you compute how much of the vector V is in the D direction. I have a picture coming shortly. So that's the general formula. I won't explain, except show you where it is. Sorry, where is the general formula? Yeah, so I applied the projection, but let's look at what's happening. So we have the direction D, here shown in black, and then we have the vector V. So that the green part is the projection of V in the D direction. So, imagine passing a perpendicular line to the direction vector, and then you say, where does it go? Also in chapter 5 are coordinate projections. So, how we talked about basis earlier? Now we're going to talk about it in a lot more details. So, what is a basis, the different types of bases, and how do you do the change of basis? So, it's important details. This is how you change a basis transformation. When you have one vector expressed in respect to basis B, and you find its coefficient with respect to another basis. Now, chapter 5 also has some more theoretical aspects about vector spaces. So, one way to describe a vector space is as follows. So, instead of, you have one vector, you have another vector, but when a vector space is it is the set of all vectors that can be written as linear combination of these two vectors. So, mathematicians came up with a nice short operator called span. So let's say I have n vectors, v1, v2, up to vn, and I say the span of these vectors, what it really means is any vector that can be written as a linear combination, so alpha 1 times the first vector, alpha n times the last vector, for any coefficient. So what does that mean? So let's say you have the x-axis and the y-axis. Well, any linear combination will give you the whole plane. So that's how we talk about vector spaces. It's not just one or two vectors, but it's not sets of vectors, but the whole any vector that can be expressed in terms of these. So I won't talk about much more here. It's just you're starting to get into a little bit more theoretical territory where we're talking about planes and lines as vector spaces. Also, certain properties of matrices can be described as vector space, like the column space, the row space, the null space. So we'll talk about that. Another topic is how to find a basis. So when you talk about vector spaces, it's really important to have a basis for them. I could give you just some random vectors and be like, hey, is this a basis? So that's what this chapter, this section 5.5 is about, is again, leveraging the Gauss-Jordan elimination procedure you learned in chapter 4, you can do some useful calculation and find a basis for any vector space. So that's an important technique going forward. And this concludes chapter 5. So far we've studied computational techniques and geometrical techniques. Now this was all a setup. Because the real object in linear algebra, as we said in the beginning, is the linear transformation. But if I just jump to chapter 6, I would just be stating definition. But now we have, on the one hand, we have computational techniques that you can handle. Like if I ask you to compute stuff, properties of a matrix, you have it. At the same time, you've seen some geometry. Now, this is both pictures you have to keep in mind and merge to really understand what linear algebra is all about. And what is linear algebra all about? It's about linear transformation. So vector functions take n-dimensional inputs and produce m-dimensional outputs. Here is a picture, right? Mathematicians like to have this high-level picture. You have some input vector space, V, and you have the output vector space. And the linear transformation takes this input vector and produces this output vector. And what's linearity, in the next picture, is that imagine I have this vector V1 and this vector V2, and I know where the outputs are. And then I take the inputs to be 1/4 of V1 and 3/4 of V2. So it will, imagine there's like 4, in the distance between V1 and V2, it will be here. It will be 3/4 of the way to V2. So the fact that it's a linear transformation, what it tells me is that the output of this linear combination is exactly 3/4 of the way towards between the two outputs. So this is extremely powerful technique to know about linear transformations, and it's kind of the whole reason why we use them so widely. The next thing, this chapter is mostly about not just defining linear transformations, but using them, and this relationship between a linear transformation and its matrix representation. So rather than theorize about it, I show a lot of examples. So this is the projection onto the x-axis. So whatever point you are, after doing the projection, you have to be on the x-axis. This is the projection onto the y-axis. You have rotations, so that's reflections. Then we have reflections through an arbitrary line and rotations, which are the most interesting. So we're really going to learn about all these transformations and their matrix representation and how to find inverses and so on and so forth. Now, this is a little bonus chapter, which probably goes beyond what you would learn in a linear algebra class, but I care really deeply about basis. So we really make this clear here in section 6.3, what exactly is going on. Okay, so that's kind of the end of we've reached the first checkpoint. So up until now, we studied all these things in isolation, and it was a lot of different properties all at once. Now, in section 6.4, this is a key checkpoint which goes through everything we've seen until now. So from systems of equations to columns, row spaces, reduced echelon form, and we combine them into one big theorem that really combines everything you've learned until now. So the whole point of this theorem is to distinguish. We said there are all kinds of matrices, and certain matrices have an inverse, and certain matrices don't have an inverse. So it turns out when a matrix has an inverse, it has all these 10 properties. And as the opposite, if it's not invertible, then all these properties don't hold. So it's a good review section, and there is some proof. There's some proofs here, so that will give you a little bit of a theory boost. So in case you get asked something like that on an exam, you can handle. But with this, we conclude the chapter 6 and the core material. Now, chapter 7 is more like bonus. Is the beginning of a bonus chapter. So you know about linear transformations, then you know linear algebra. But now, what if we can add some more? And in particular, one of the fundamental ideas is the notion of an eigenvector and eigenvalues. So if a matrix A has an eigenvector, then an eigenvector B is this. So you multiply A times that eigenvector, and what comes out is the same eigenvector times a constant. So that's really interesting, because usually a matrix will change the vector in an arbitrary way, right? When you multiply, it could rotate it, it could reflect it. But there's this specific vector called, in German, eigenmean self, or this is like a special vector adapted to A that will just get scaled. So let's just look at an example. So this is some arbitrary matrix. If I multiply it by the vector 1, 0, I get the vector 1, 5. So this is not a multiple of this. But what if I multiply it by the vector 1, 1? Well, it comes out as 6, 6. So that's 6 times what I input. So what this tells me is two things. So one is that 1, 1 is an eigenvector, and that the lambda, the eigenvalue, is 6. So you cannot just guess the eigenvectors. There's this specific technique. So first you have to find the eigenvalues. which is done with this determinant calculation. Or you can just call the matrix has an eigenvalue. So this says -4 is an eigenvalue with multiplicity 1. You can also find the eigenvectors. So you see this is the eigenvector with eigenvalue 6, and -1, 1 is an eigenvector with eigenvalue -4. So I won't say much more except to show that once you have these eigenvectors, you can put them in a matrix, and you can put the eigenvalues in another matrix on the diagonal, and then you can write A as a decomposition of Q, the matrix of eigenvectors, a diagonal matrix of eigenvalues, and then Q inverse. So this is useful in many situations, but we won't talk about it much. That's the subject of chapter 7 in great detail. Then there's some bonus material where just terminology, when you read papers, when you read science papers, they always say, oh, A is a diagonal matrix. So that's what diagonal matrix looks like. Upper triangular matrices, orthogonal matrices, these are just definitions of special cases of everything we've seen until now to get you comfortable with certain permutation matrices. It's just terminology of things you've seen until now. And this is a nice useful summary of what happens, which matrices are what, and what that means. All right, so we're almost done now. The abstract vector spaces. So up until now, when I said a vector, you could imagine a little arrow, the geometrical intuition. But it turns out there's a lot of other math objects, like polynomials, functions, that behave like vectors. So what does it mean to be a vector? Is to obey these 8 properties. So if you can add together vectors, if you can scale them, then you are vector-like. So let me give you an example. For example, the polynomials. Look at that. So this is a polynomial of degree n, and as far as we're concerned, this is a function. But if you ignore the x's, you can always talk about this as just a coefficient, 0, a0, 0 to an. And imagine I add 2 polynomials, right? What will happen? I have to add the constant terms, add the linear terms, and then add each power, the coefficients of each power. So that's how you add vectors. So we're talking about polynomials, but the math, the algebra of we will do with vectors, we can actually do it with polynomials. So at some point we stop caring about what polynomials, whether it's polynomials or vectors, we talk about this, it's an abstract vector. So we can talk about dimension, we can talk about the basis in the space of polynomials. So that's what this chapter is about. And furthermore, in the next chapter, we introduce the notion of dot product or inner product for vectors. And then we can talk about orthogonality. We can see this coefficient, this polynomial is orthogonal to this polynomial. And let's go back to the polynomials. For example, this would be an inner product for functions. So these polynomials form an orthonormal basis. So really useful in physics, differential equations, and so on. So this kind of concludes everything I wanted to show. Oh, there is some more. So this is a computational trick. When you're starting with a bunch of bases, with a bunch of vectors, how you can make them mutually orthogonal. Let's say the vectors are just pointing some of them in the same direction. What you do is you take one, and then you take the other one to be perpendicular to it, and then the third one perpendicular. So you have to know this. It's not super exciting, but it's a nice procedure that you can follow for obtaining an orthogonal basis or an orthonormal basis. Then there's some more vocabulary and generalities where you decompose a matrix into different types of bonus stuff. Don't worry about it too much. Now this one is really important. So up until now, everything we did in linear algebra was with real coefficients. But what about complex coefficients? So complex numbers are first introduced in the vector chapter, so section 2.4. And then we don't talk about complex numbers up until now. But this section here, 7.7, is a great review, because everything you learn about linear algebra, now we have to revisit and clarify. So instead of being a vector of real coefficients, now it's a vector of complex coefficients, a matrix of complex coefficients. So it really helps to go over all the material, the transpose, all the operations, linear transformations. It's a nice review, and it really shows what is general and what was specific. So by the end of this, we have row operations. It's a nice review. So what I'm talking about is, let's say in your class you don't have to take complex numbers, linear algebra with complex numbers. Still, I would like you to read this chapter, because that's your review. If you look at it's a little bit foreign, but it will give you the contrast of what you already know, because it's all in one place. It will be a nice review. And also, yeah, bonus stuff here too. All right, so that's the book. And that's a video of 51 minutes. Wow, that's abusive. Now you know linear algebra. That's all there is. That's what's in the book. The book actually continues with 3 chapters of applications, but we'll talk about that in another video, because this one is already too long. And I encourage you to check out the book and you can find from the website the concept maps, which show the connections between all these things I talked about today.
These are in the front of the book. You can find them in the PDF preview. And this notebook will also be available online at no. I will just show that. .com. No BS notebooks. Nope. So this video will be posted somewhere here shortly. And that's your No BS LA notebooks. All right. Thanks for your attention, and I hope this wasn't too bad. Bye, everyone.